under the same name. Okay, it's live. We're good. Should be popping up here in a second. Okay. Well, either way, we'll, I don't know. So we'll just continue on here. Let's see. Yes. Okay. So we're going to learn a little bit about relativity, and then we'll look at some experiments and analyze it through the relativistic lens and see what we can come up with here. So to start us off, our guidebook is going to be Einstein himself. Now remember, his theory of his mathematical theory is the same as Lorentz's theory, which is the same as Voigt's theory. And these were derived under the premise of an ether theory, where they were using timing and spacing of waves with respect to an elastic medium. Now, an important thing that Einstein distinguishes here is that he's not going to use a luminiferous ether as a physical mechanism or as a mathematical reference point. Everything is going to be relative motion between source and observer. All the examples he gives in his paper go on to describe, clock A and B. It's never clock A and B with respect to, the midpoint of Earth or something like that, right? So the core postulates here that he asserts for his theory is that uniform translatory motion produces no first-order effects in mechanics and electromagnetic processes. You can read that right here where he talks about the first order of small quantities. The laws of electrodynamics and optics are valid for all frames of reference in which the equations of mechanics holds true. So in other words, if you take the scenario where you're stationary and then, F equals ma applies to you, you can make all the correct predictions, all the correct dynamic predictions. If you were in a train, right, if you were in a closed system that was in uniform motion, you wouldn't be able to tell without external reference that you were in motion. So they're asserting that the equivalence there is that, you can be in motion uniformly and you can't use light to differentiate, and his equations are going to hold true here. There's not going to be any first order effects of motion because they tried to measure things like aberration when they introduced water. They were looking for a deviation, and that would be a first order effect in the V over C relationship. So here Einstein's coming in to explain a V squared over C squared relationship, but we'll get to that as we continue for the second order stuff. But primarily here he's saying that the important takeaway here is to the first order. He's saying that if you were to try to measure using light uniform motion, you wouldn't be able to do it. And he asserts that all inertial frames are equally valid. And this is important because the mathematics of the framework, right, depends on symmetry and reciprocity between frames, meaning there's no preferred frame, because if there's no ether frame and everything is going to be described through the relative motion between source and observer, then you need to be able to show the reciprocal effect in the other frame, right? So in other words, if you have a clock moving around the Earth and that clock experiences retardation to the square of its velocity over c squared, then also the stationary clock in comparison, it should also, have that same retardation. Otherwise, there's a preferred frame, and you could tell that clock was in motion relative to the stationary clock. There's no equivalence there. So that's where you get into the twin paradox and all that stuff, but we don't have to go there. But that's just kind of the fundamentals of explaining like what Lorentz symmetry is, what it means to merge space and time under transformation. Both of the coordinates have to be moved symmetrically. And under this framework, the speed of light is independent of the source and receiver. And we'll get into what that means and how he derived this and how it applies. But this is just further asserting that under these principles here, that the speed of light is the same, and you can't use it to measure relative velocity. And then he, makes pertinent here to remove the ether as a physical substrate, a mathematical point, and a philosophical reference in favor of space-time geometry. All right, any questions so far about this part?
Yes, I have a question. You
Yes.
said that a clock, if I put a clock in a plane, um, if I fly, for instance, one of the early experiments done in the 1970s, they flew atomic clocks in planes
Mhm.
twice eastward and twice westward around the Earth, and then brought them back and compared them to a stationary clock. You will see a difference then, right?
Yeah, that would be a one-way measurement of it. Remember, the theory requires reciprocity between the frames. So, although they did get the one-way measurement, that's indistinguishable from the classic theory, which predicts that relative motion, through a field or what have you, would produce retardation to the proportion of the velocity. So, it's indistinguishable in that regard. That's where you get into the twin paradox and stuff. That's what I was saying. We don't have to get into that too far.
Well, what you're saying doesn't make any sense. Classical theory doesn't predict clock retardation at all. Clock
Uh,
retardation is entirely relativistic, right?
Oh, no. That's called the Sagnac effect. And actually, what's shown to be the correct formula to do atomic clock correction is the Sagnac formula.
That's also not true.
Well, as I continue, why don't you look that up, type Sagnac effect in atomic clocks, and see if we can come back to that as we continue on.
Yeah, let's move things along, and then we'll come back to maybe that point of discussion. Go ahead, Alan.
Yep, no worries. No, I mean it's a good point of contention, but I can show all the stuff for that, but we got a little bit to get through here. So just take me at face value for a minute. All right, so simultaneity is defined. So this is an important distinction here, where simultaneous events are being defined as not simultaneous as a consequence of the constancy of speed, and of the consequence of the speed of light. He goes on to give an analogy here about how the local time in which a train shows up when his clock hits the 7, or strikes the 7 hand, or when the hand on his clock strikes 7 o'clock, and a train miraculously appears. That 7 o'clock reference doesn't mean anything to an observer who isn't in the same time zone as Einstein. So, in other words, time has to be locally defined. And he goes on to say that we have to throw away the concept of simultaneity applying in both frames, essentially. And again, with the reciprocity, you would have to have the simultaneous event, not occur in one frame so that it can occur in the other. So that when you do the transform, you could show the inverse, where the outcome would be it was simultaneous in the moving frame versus not simultaneous in the stationary frame, which I know sounds antithetical, but that's what the whole premise is built upon here. And then, so local coordinates have to be defined by the observer and the source, right? So that we're not going to use fictitious midpoints or anything like that. And then relative simultaneous events allow for reciprocal transformations. Okay, and then he gets into the thought experiment, which is the train experiment with the midpoint and the speed of light with respect to two events occurring simultaneously at the either ends of the train, and which will be perceived first. Now, obviously, this the classic theory says that the event is simultaneous for both people, but as an apparent effect, it appears for the moving observer that it's not that the event didn't happen simultaneously. Now, this is where Einstein differs, because it has to be physically different, because we're discontinuing, because there's not going to be absolute time and space. It's going to be relative to this localized instant. If the chain of events isn't causally linked, then they're spatially separated. They're therefore not connected in terms of series. So if we were to make both frames agree to the simultaneous event, like the classic theory would, you'd be using absolute time and space. So let's see. So we get into relative lengths and time. So using an assumed constancy of speed of light here, Einstein shows that the clocks in relative motion to one another would measure different times, different distances for their rods, the difference being with their velocity with respect to c. So how do we fix that? 1 second, I'm going to hit some water here. So real quick, if we use an arbitrary midpoint here for symmetry, we have this relative motion described, then the speed of light is going to be measured, plus or minus v, essentially. And Einstein's saying, well, that's not going to work, because in my theory, the speed of light is going to be constant for these lads. That's what we're going to be using for our ruler. These guys can't measure different lengths of their ruler. It's not going to lead to a coherent theory. So what's the answer? Well, in order to make C plus or minus V not that and make it equal C, you have to offset it by the coordinate system difference. So instead of C plus or minus V here, he's going to turn that into length contraction and time dilation, because time and space are a function of the square of velocity squared. That's what the coordinate system offsets. So the coordinate of time and the coordinate of distance gets offset by a function of the velocity to make the contraction happen, to make the constancy of speed of light work out mathematically for them, so that this situation here where the measured difference goes away using absolute time and space. All right, so another important distinction here is relative motion in any closed polygonal circuit or continuously curved line will experience the second order effect of 1/2 times t times v squared over c squared. So this is going to be the difference that we were talking about earlier with the atomic clocks at the equator completing a round trip. They should experience time dilation with respect to that in a closed circuit. And then if these equations hold true with reciprocity and the transformations, you should be able to show the reciprocal effect in the stationary clock. But that's never been done before, and that gets deep into the twin paradox and stuff here, which is kind of outside of the scope here. But it's just to reiterate the significance of reciprocity in the mathematical formula, or like in the philosophy, because it's not just part of the philosophy, it's in the math for a reason, for the symmetry. So it's important to understand that moving forward, because when we're going to look at some experiments, we're going to see some asymmetrical transformations, and we need to understand what the rules are to point out the violations. So frame equivalence demands reciprocal relativistic effects being measured in all frames. Otherwise, we can tell that there's a preferred frame. If this one's not experiencing relativistic effects, why? All right. And then so in a closed polygonal loop, there's no relative motion between 2 points that are fixed. So he's saying that if they're in uniform transitory motion, these equations should apply. Now, although people will say, a Sagnac interferometer is rotating, it's a non-inertial frame, what he's explicitly deriving here is logically consistent with relative motion with regards to it being in a closed loop and uniform transitory motion, because if you zoom in on any portion of that loop, it's effectively a linear path and it would apply. So let's see here. All right. Here we go. All right, now, in addition to that, we have the rules for velocity composition. So previously, the classic theory was Galilean. So what that means is you could just do the old C plus or minus V, and you'd be good to go to make your predictions. So you're just adding the velocity to the speed of light or subtracting to it to get the difference, and you're good to go. Now, Einstein says, nope, speed of light is constant, my dude. So what you're going to do is divide by 1 plus the speed times the speed of light divided by the speed of light squared. And that's going to basically ensure that it always works out to be the speed of light. You're never going to exceed it when you're using values that are slower or, much slower than the speed of light, or even when they go faster, because the way it scales, it always comes out to be the speed of light. So, and that's an important distinction to make, because remember, classical physics, like the Newtonian classical physics, is built on absoluteness, being able to do things like mass addition, velocity addition, things like that, using this reference point. But Einstein's saying, no, you gotta Lorentz up, and you also have to make it so that the speed of light is always the speed of light. So this isn't anything that was ever empirically measured or anything like that. This is just, he's mathematically just, imposing this to make it work out, to maintain the postulate of the symmetry.
True, though, is it?
What do you mean?
When you say that it's never been mathematically demonstrated, that's not true.
Well, we can get in. We can get
can-
into measurements as we go forward. And we certainly are.
Okay.
Mathematically demonstrated is a bit of an oxymoron, don't you think?
Well,
Yeah, because
there,
that is.
there are observations that accord with the mathematics, right? So
Yeah,
the
we can get into
mathematics
those.
have been observed to apply in reality.
Yep, we can absolutely get into that. No, you're good. You're good. It's okay.
Yeah, let's table that and let's keep moving, I guess. But yeah, good.
Yep.
Good point
Okay.
of conversation for later.
Okay, so starting off with old Sagnac in 1913, he comes around. He goes, okay, so we got this theory here that's making certain assertions about closed polygonal circuits in uniform rotation. So I have this turntable here that rotates at 13 rotations per minute, and I'm going to use a split light beam, and it's going to complete a circuit going clockwise and counterclockwise with respect to that rotation. And we're going to see if when the light beam recombines, if it measures the relative motion of that rotation between these 2 points, the source and the observer, that are fixed and moving at a constant speed. And by Einstein's definition given in his theory, these equations should apply and there should be no fringe predicted here. Or at the very least, there should be a much, much smaller fringe because of the theory being built on second order effects of link contraction and time dilation. There might be, that effect, but that's much smaller than the first order V over C relationship that is measured with Sagnac here. So what was actually measured was that exact first order relationship here. So when these light beams recombined, they were out of phase, and the what's the word I'm looking for? The fringe pattern, right? That destructive interference pattern, the little black spots, the length of those, right? The square of that is proportional. The square of that distance of that length is proportional to the angular velocity of this rotating disk. And that's what Sagnac measured. That's what the interferometer picks up. That's the relationship with the fringes to velocity. And relativity theory is predicting that there should be no fringe here. So Sagnac was like, hey, existence of the luminiferous ether demonstrated by means of relative ether wind in a uniformly rotating interferometer. So the way that Sagnac conceptualized his explanation for this was saying that there was a greater ether, right, that was like encompassing the Earth, and then local motion within that would generate its own optical vortex, which would cause the retardation or acceleration of light with respect to motion in that vortex. That's how he explained it, and that just gives the C plus or minus V. And in frames where Einstein is saying that his equations should apply and there should be no detectable fringe. Any questions on this experiment? We can get into some questions now. Now that we've laid out the groundwork and stuff, we're getting into some experiments. We can have some back and forth on the experiments for sure.
Okay, so I dispute the claim that relativity says that there shouldn't be a fringe here.
Okay.
I don't think that is a fair summary of what relativity predicts.
Okay. 1 second.
If V over C is small, then we predict exactly the same as the classical formulation, and the Sagnac formulation in its simplest form is exactly in agreement with the classical formulation. You don't need to introduce relativity to predict that there will be a fringe effect. So the fact that you get a fringe effect is not in disagreement with relativity. And I'd like you to produce a citation that says that it is, if that's what you're claiming the paper produced.
Okay, sure. We'll start with that first, and then I'll get into why it's a violation. 1 second. GPS 4. Okay, so here we have Post from 1967, and he's giving his analysis on the relative motion between the source and detector. So if you try to apply a Lorentz transformation between the relative motion of the source and detector, right, you're looking at two inertial observers, and inertial observers, as we know from the theory's postulates, measure the speed of light as constant. So this is what Post says about this situation here. To be consistent,
Can you read the last 3 words of that sentence?
To be consistent with the principle of relativity, one has to demand that the Sagnac interferometer and the ring laser cannot lead to a fringe or a beat frequency in equipment in uniform translational motion.
So Sagnac's rotating his equipment. It's not in uniform translational motion.
Ooh, so an atomic clock around the Earth in relative motion to a stationary clock is the same exact concept. It's just on a bigger scale.
No, it isn't, sir. And just asserting things doesn't make it true. I asked you for a citation saying that relativity predicts that there should be no fringe shift here. You just showed that that is the case for a uniform translational motion. This is not uniform translational motion. The whole point is that it isn't uniform translational motion, that it is a rotational motion. So
Okay.
can you tell
What-
me,
yes.
you provide a citation saying that there will be no fringe shift if the apparatus is rotating?
Yes, we will look at the 1 second. We will look at where is 1 second before we move on. Here is Ashby. Here we go. Okay. So this is Neil Ashby trying to explain how the Sagnac effect is measured in GPS and how it's a relativistic effect. He says observers in the non-rotating ECI inertial frame would not see the Sagnac effect. Instead, they would see the receivers are moving while the signal is propagating. So what he's saying there is that in our frame, we should not see the speed of light difference, yet we do. It's
No,
what's measured.
That's not true, sir. We're not in the Earth-centered inertial. We are rotating with the Earth. We are in Earth-centered, Earth-fixed coordinates. We're not in the ECI reference frame.
We're in the
That's the
ECEF
type-
frame where the measurement
The
is made,
ECEF
and
frame
and
the
that's.
ECI and the
Please don't,
ECEF frame.
hey, buddy. Please
Hold
don't
on,
talk
hold
over
on.
me
Hey.
when I'm giving my explanation.
Yeah. If we could
Okay.
try to avoid over talking, just
Yeah.
one at a time, please.
So
Go
the
ahead.
measurement is made in the ECEF frame. He's talking about what an observer in the ECEF frame would see. So if you're in the ECEF frame and you're looking out at the rim of the Earth, an observer on the Earth is measuring the speed of light being constant. Or I'm sorry, would see the receiver moving while the signal is propagating. So he's chasing the speed of, dude, Tony, you're trying to talk over me, bro. Like, just relax. So in this respect, it's predicting no fringe in this as well. Now we can get back to the actual measurement here, right? 1 second.
Well, hold on. Can you clarify your point, Tony? Because I'm not sure it's clear to everyone what you're saying exactly.
So the Earth-centered inertial frame is a reference frame in which you're on a point just above Earth, but the Earth is rotating underneath you. So you're not rotating in the Earth. So you're basically in free fall with the Earth around the sun. That is the Earth-centered inertial frame that guy was talking about in that quote. The Earth-centered, Earth-fixed is what we understand every day. It's the reference frame in which we are rotating with the Earth. So he's saying that you would see different things in the Earth-centered inertial frame than you would see in the Earth-centered, Earth-fixed. But we are in the Earth-centered, Earth-fixed. So saying that there would be no fringe shift in the Earth-centered inertial doesn't have any relevance whatsoever to what we observe where in the Earth-centered, Earth-fixed reference frame.
They wouldn't see us seeing the fringe is the point. That's the big point of contention. That's why this guy here post is saying that. Now he's talking about uniform transitory motion. Please, you know what?
2 minutes ago.
Tony.
Yeah.
Stop it, man.
Your big point of contention was that this is rotating and that's not allowed. That's why I specifically went over at the beginning where Einstein says, hey, if you're in uniformly okay, here, we'll just read the whole quote here because maybe it wasn't clear. It is at once apparent. He's talking about clocks A and B, one clock A going in relative motion around the Earth to B, experiencing retardation to the factor of 1/2 times t times v squared over c squared. He says, it is at once apparent that the results still hold good if the clock moves from A to B in any polygonal line, and also when points A and B coincide. If we also assume that the results proved for any polygonal line is valid for a continuously curved line. Okay, so if it's in uniform transitory motion, that's the point. So if this interferometer is locked in at 13 RPM, it's in uniform transitory motion. Now, there's a whole entire measurement we can get into that's linear, but this is the issue with respect to describing the Sagnac effect in the confines of relativity, which you specifically ask for. So if you were to apply a Lorentz transformation to the detector that's in motion relative to the receiver and on the platform, even though they're fixed, right? And you apply your Lorentz transformation to the receiver, which is the recorder on the platform that's rotating too, you do not predict a fringe pattern. And at best, you would predict a much smaller fringe pattern. That's what this guy is saying. It cannot lead to a fringe, in plain English. Oh, you can speak now.
He's talking there about uniform translational motion. A rotation is not a uniform translational motion, and simply asserting that it is just mendacious.
What's this right here that Einstein says from his own theory to illustrate that? What is that? Can you read this real quick out loud? I might have trouble seeing it.
I can't see which bit you're pointing at.
Here we go. 1 second. We move these over here.
Hey, really quickly, Mordawan, can we not throw accusations of lying and stuff? It's very
Hey,
childish.
Hey, hold on a second. Lily, it's fine. It's fine, Lily. Can you read this out loud here, what we're talking about?
The bit in pink, you've already read it. It is once apparent that this result still holds good if the clock moves from A to B in any polygonal line, and also when the points A and B coincide. But while that is true, if you are moving along a polygonal line, you are undergoing accelerations, right? So that formula there does not include the effect on time of any accelerations that you have undergone in tracing a polygonal line. So that the line of argumentation that you are trying to construct here, there is. Can you please cite me somewhere a textbook that says relativity predicts that the Sagnac effect should not occur?
Would you say a textbook? Obviously, there's no textbook that says that, but I have papers from people that are just because people are discussing it. When you apply the theory actually to how it's supposed to light, to relative observers in motion, it doesn't give the correct measurement. So you want a linear measurement. Great. So here,
no, I don't want a linear.
Yeah, you said you want uniform transitory motion.
No,
We're moving. We can move on now to the uniform transitory motion experiment.
Ruyong's Wang's paper. I noticed that you didn't put up the citation here. Okay, you did down the letter. But this paper has been debunked. It's
by
been
who?
Torn apart by Clive Wells, among others, has done a paper arguing against the fact, and indeed,
Cool. We'll read it live. We'll read it live at the end of the Prezi. We'll see what his relativistic treatment of it is.
That statement there, the linear motion of the top arm of the sensor is detected with a phase difference delta phi. That violates the main principle of relativity. You cannot detect a linear motion from inside the system.
Agreed. And yet we're looking at a graph of linear motion being measured.
Wang is wrong.
What? We're looking at a measurement of linear motion being measured.
No, we're not. We're reading a paper where Wang has misunderstood what he's done.
Oh, okay? So wait 1 second. Let me kind of explain something here. So we have a stationary source emitting light. We have a stationary detector, right? No relative motion between these lads. We have a total length of a fiber cable here, right? We're using the effective length, only this moving portion. This portion at the bottom is stationary and fixed. These two arms that wiggle cancel out, so we don't count these. So the only distance we're counting is this delta L here, the effective length and the velocity that as we move this back and forth. Remember, source and detector, stationary AF in the lab frame. So we're looking at a fringe pattern measured here with respect to what? This graph is showing linear motion being measured with respect to what?
With respect to the laboratory reference frame, is that what?
So C plus or minus V with respect to an inertial observer?
No, it's the distance traveled traveled by the beam is affected by the velocity of the various receivers, right?
I mean, not according to relativity theory. If it's in uniform motion,
the light that's changing, it's the distance that's changing, and that distance is changing because of the
Oh.
velocity of the receiver.
Well, remember here, Einstein says we're not going to use absolute stationary space, so you can't preserve the distance length. The speed of light has to traverse the circuit without preserving any distance change. Otherwise, if it doesn't, then it would produce a fringe pattern, and then you could measure linear motion, and relativity would be false, which you correctly deduced from this equation here, and in its significance.
So, but no, that's not what he said. He said that if the receiver is moving, that does impact the amount of distance that if a receiver is moving towards the light source, then the distance that the light has to travel in order to get to that receiver is less than if it had been stationary or if it had been moving away from the transmitter. Right?
Yeah.
That's just a fact of motion.
If you use
so
the
velocity
Tony,
of the receiver is important in the distance traveled.
But Tony, do you understand that in doing this, you would have to invoke a fictitious midpoint to preserve the distance, which would be using absolute space? You would be using lab time and lab space to describe the fixed distances of the interferometer to describe the distance change.
True, sir. That's absolutely not true.
It's explicitly true, and it's the issue at hand.
No, it's not explicit.
This to conjecture, and this is about the principle, all inertial frames being equally valid. If we raise this to conjecture, this will be hereafter called the principle of relativity to the status of a postulate, and we will also introduce another postulate, one of which is irreconcilable from the former, namely that light is always propagated in empty space with a definite velocity of c, which is independent of the state of motion of the emitting body. Now, Tony, before you jump to conclusions and say, but he doesn't say receiver here, right? Unless the implication, number one, is receiver, he's not saying anything new about physics, right? Because the classic theory would predict the relative motion. You would measure the velocity of the wave, c plus or minus your velocity. But this is a deviation from that. So, and then all the examples he gives in his paper are relative motion between clocks A and B, thing A and B, etc. Right? It's not A and B in some fictitious midpoint or something like that.
So if you look up the very derivation of the Sagnac effect, you will see that it involves the velocity of the receiver.
Oh, that in the classic theory, yes.
So in the very derivation of the formula, sir, and your claims, you seem to be sort of tiptoeing around the fact that at its principal level, no, Einstein doesn't agree with you. Einstein agrees that the time it takes for light to travel a given distance d is always going to be consistent with it traveling at speed c. But that distance in and of itself can be affected by the motion of the receiver. If I move the receiver closer to the source, I receive the signal earlier than if I move the receiver away from the source. This is simple physics, sir.
Okay. All right. We will come back to that in one moment. So we have Professor Jody Cooley here. She has a little prezi on relativity as well. And she just makes it clear here, Einstein's postulates, the laws of physics are invariant for observers in different inertial frames. And the speed of light is the same to all observers, regardless of their motion relative to the light source. Super important there. And then, so if it's irrespective of that, then there's a distance change, but the speed is the same, then it's going to traverse the distances at the same time and recombine and be in phase and not produce a fringe.
That's not true. That's simply not true. Again, so what's happening in the Sagnac effect, when you rotate the apparatus, one of the mirrors is moving towards the source, and one of the mirrors is moving away from the source. It takes the light longer to get to the mirror that's moving away from the source, but it takes less time for it to get to the mirror that is moving towards the source. This is the entire point. So to claim that the mirror motion has no effect on the distance that the light is traveling by the time it gets to the mirror, this is just confounding all of physics.
So-
it clearly does have an effect, and that effect is exactly in accord with what is produced when you do the experiment.
So here, Einstein is saying, if you're C plus or minus Ving, you're not doing it right. Remember the constancy of the speed of light here, right? We're not going to have a situation that's going to lead to C plus or minus V. We're going to use Lorentz transformations. And on top of that, right, even if there were a case somehow where there was C plus or minus V, we're going to use velocity composition to make it not so. There is no case in which, one second, there is no case in which an inertial observer, these two detector sources being stationary, should measure the relative motion of this length of the cable.
Your test case there, that example that you're using, in that case, the light is propagating orthogonal to the motion, right? It is not. That is not a case where the receiver is moving directly towards or away from the light, which is what is happening in the Sagnac experiment. The mirrors and the receivers are moving towards or away from your photon source.
Tony,
So that's very different. That's very different from what Einstein is considering about a clock that is using backwards and forwards bouncing of light to measure time.
well, Tony, you know that he did another configure.
You're trying to use the derivation of time dilation to argue that moving a mirror towards a light source or away from a light source has no effect on when the mirror intercepts the light source. That's absolutely untrue. Einstein doesn't believe it. No relativist that believes it. You're just misinterpreting the literature here.
Okay. So to start us off here, he did different configurations where the source and detector were also in motion parallel to that, where the theory would predict no motion between them as well. And it still made the same measurement. So that's not valid. That's not valid either. And hold on a second, man. You just spoke for a minute here, and you said that I was trying to assert that time dilation accounts for this. That's not what I'm asserting. That's what Einstein's asserting here with this retardation coefficient here applied to his A and B clocks. So if we took A and B and we applied that coefficient here, we would have a much smaller, we would predict a much smaller measurement. We're not making the correct prediction here. So there's no way that you're able to rectify this. We have a situation too where the source and detector are moving parallel with the conveyor's configuration. And relativity predicts no fringe for that either. 1 second now. Let me turn you back up.
You are just asserting that relativity says this, and every time you've tried to produce a citation to support your contention, it has been shown that it is not referring to rotation. It is referring to uniform translational motion, or it is referring to a different reference frame, the Earth-centered inertial, as opposed to the Earth-centered Earth-fixed. And you are claiming that Einstein's description of time dilation, which is the example that he's using there, relates to the Ryu-Wang, let's just call it the Wang paper.
Well, it would relate to a Sagnac interferometer. Don't steel man me. Be consistent.
Or
straw man me, sorry.
Again, you did ask that I not interrupt you.
Apologies.
But it is not the case that what Einstein was describing there. Einstein there was describing a very particular case, and it is not the case that Wang's paper is describing the same case. So you are taking a result from one theoretical formulation and applying it in a different theoretical formulation where it does not fit, where it should not be invoked.
Well,
guys,
I've got to go.
Go ahead.
But anyway,
okay.
that'll probably facilitate this presentation.
Yeah, I was trying to meet.
I suggest you talk to a relativist about this because you seem to me to be getting a lot of stuff.
Okay. Thank you, Tony, for participating. We have so we do have a voice queue in the server, which I just directed people to. Looks like Jesse is next up on the queue. So if you're ready to go, Jesse, take it away. Unless Alan, you wanted to address anything else first.
Yeah, real quick, I wanted to say here so this is extremely important in regards to using the preserving that length for the distance change, right? Because that's the use of absolute time and space for the comparison. And Einstein is specifically saying here, which he's deviating from the Lorentz ether theory, which this mathematical framework is identical to, but he's saying here that like this theory is different from this. And this, so how's it different? Ian, tell us how. The introduction of a luminiferous ether will prove to be superfluous in as much as the view here to be developed will not require an absolute stationary space. Okay, so we're not going to use any fixed points. We're not going to preserve how far that mirror moved relative to when it was fixed in the lab, right? Provided with special properties, nor assign a velocity vector to a point in empty space in which electromagnetic processes took place. So wait a minute. If the mirror is in a physically different location, and as a relativist, I use some midpoint to preserve that location to describe the distance change. So I can have this effect, C plus or minus V, which is explicitly said that we're not going to do, and we're going to facilitate that via Lorentz transformation. Then the theory is violated on the principles of it. And we'll get into some people trying to do a derivation of it real quick. Let me see if I have that one queued.
Hold up, though. Can we get Jesse to jump in real quick before you get to that?
Yep, go ahead.
Oh, thank you. My question was, did you say that Wang et al. Did demonstrate a shift within the same inertial frame?
What do you mean? What are you saying?
Yeah, I mean, I'm aware that he showed the Sagnac effect between two different inertial frames connected by fiber optic loops in his trapezoidal thing. But I thought I'd heard you say that he had showed or implied that he had showed the Sagnac effect taking place in entirely within the same inertial frame. But maybe I misunderstood.
I'm confused about what you're talking about. I'll reiterate what he measured though. So he did one configuration where the source and detector were co-moving together with a conveyor configuration. So this portion up here would be moving at the same time as these detectors, and it measured the velocity of the cable, as it's rotating or going around the conveyor, the linear portion. And then he did this configuration here where the detector and source are stationary, and just this portion up here moves. Now, the important distinction of this is that if it were relative to the whole, then it wouldn't just be relative to this loop section here. They would have to use the full length of it. So that's extremely important, because what is this section moving relative to, right? These two are inertial lads. There can't be any relative motion here. It's just moving back and forth in a straight line.
Oh,
Anyway,
okay. So
does that answer your question?
So the upper and the lower portions of the fiber loop were in different inertial frames, right?
The bottom part is stationary here, right? So it doesn't predict any fringe difference, right? The wiggly arms are the same length here, and they both cancel out when they're moving. So we don't count any fringe here for this, and then they just counts this top portion that's moving. So if it was relative to any other part, what I'm saying is that you would also have to incorporate that length.
Okay. So can I ask one other question?
Mm-hmm.
Thank you. You quoted a lady who said that the laws of physics are the same within different within different inertial frames. Are you saying that she's saying that across two different frames they'll be the same? In other words, if you had two inertial frames, but those two inertial frames were were moving, say, at different velocities than each other, that the speed of light between those two frames would be invariant, or is she talking
So,
about?
so you know how you can how acceleration is a time derivative of velocity. So if there's no change in velocity, the F equals ma, all that stuff, everything should apply. Essentially, is what she's saying.
But I mean, let's say we've got 2 U-Haul trucks going down the road, one at 50 miles an hour, one at 100 miles an hour. Within each truck, physics will be the same.
As long as they're in uniform motion, yeah.
But if we start measuring the between the 2 trucks, then she's not saying that also will be invariant, right?
Yes, that the purpose of it is the comparison between the two. So what you do is you're going to treat the one truck as stationary, and then you're going to measure the relative motion of that truck with respect to the stationary truck, because both trucks are moving at a uniform velocity. Assumedly, then they would be inertial frames. They would apply to Lorentz transformations.
I don't think that's what she's saying. But anyway, thank you. That was my questions.
Yeah, so if she's not saying that, then she's saying that the laws of physics don't apply in inertial frames? That doesn't make any sense.
Well, I think what she's saying is that within the truck going 50, they will apply to the people in there working inside that truck. They will act like, they will be invariant. And
with respect to what?
To the people inside that one inertial frame.
Oh, well, that's not relativity, Brody. Relativity is with respect to the other truck. That's the whole thing.
Well,
if it's with respect to itself, you're just doing classic physics. You're not doing anything new.
So, okay. Well, anyway, that was my question. Thank you.
Yep, no worries. Okay, so we can move on to some analysis trying to explain these experiments. So remember, I stated that these experiments violated relativity. They require some explanation, and it was asserted previously that they're not a violation. I should talk to a relativist, etc. Well, actually, talk to a relativist. You can check that out on my YouTube channel or the relativist's YouTube channel. You can go to I Can Science that on YouTube and type in Sagnac or generalized Sagnac or whatever, and listen to the conversation that we had. And when you apply relativity, you don't predict a fringe. I mean, he realized it pretty quick, and then tried to come up with a derivation for it, and never got back to me. But yeah, so we have a citation here from, let's see, I think this was from the.
Real quick, are you talking about the I Can Science that?
Yeah,
yeah. Oh, dude, I recommend everyone watch that.
Yeah.
And you're talking explicitly here about the linear interferometer, not general rotating Sagnac loop.
Specifically the linear, yeah. Especially with the conversation that I Can Science that and Toby and I had. So these guys,
the rotating loops is not in doubt, right?
No, but the explanation is because, again, we went over to how the relativistic treatment should be given through Lorentz transformation as defined by the theory, and yet it doesn't, because if you try to, you wouldn't correctly predict a fringe. So these guys here are all trying to describe the rotating interferometer here, but a couple of them try to describe the Wang one that we'll get into. But we're going to look at what they try to do to give a treatment here to kind of see the tricks, because what we see is we'll often hear that special relativity doesn't apply. Yeah, we're going to look at people trying to make it apply to it, because obviously you could get it to apply. And then there'll be a different explanation where they'll try and say, well, it actually falls under general relativity because it's in rotation. We have to invoke a gravitational field. And it's like, well, what does that mean? Well, we'll look at the math explanation and as a guide to see what they go through to present as explanations to try and predict this fringe to the first order. Okay, so starting with this first guy here, this is Cho. Actually, we'll come back to the rotating ones, and we'll stick to Wang real quick, because since we were just on Wang. Okay, so we have here this lad in 2016 trying to establish a generalized Sagnac explanation for the Wang experiment and the Fizeau formula. For those of you who aren't familiar with the Fizeau formula, the Fizeau drag coefficient was an experimental hypothesis by Fresnel in 1918, where he said that basically the speed of light would be dragged plus or minus the square of the refractive index of a transparent medium, and it'll share a ratio of that velocity and that retardation and acceleration. And then that was experimentally measured by a man named Fizeau in like 1856. And so Einstein says that, you know, even though his version of velocity comp in air or in a vacuum, you know, dictates that there's not going to be c plus or minus v, he basically just does, you know, regular velocity comp and then adds the gamma factor, which is too small to be or to, you know, to be accounted for, but it's in there, you know, so it looks nice. But anyway, he the Fizeau plus or minus v with the classic formula there make the same exact prediction here. And so anyway, this guy's going to generalize the Sagnac and the Wang, or I'm sorry, the Fizeau and the Wang experiment using his own derivation here. And what this guy ends up doing is he starts off with the gamma factor and then he sets it to 1, which means he cancels it out. But before he cancels it out, he grabs lab time and lab distance and he transforms that into little derivatives of his coordinate system. And then from that, he's like, look, c plus or minus v in the first order with respect to a fictitious midpoint that I made, borrowing lab time and lab distance. So remember, in the Sagnac apparatus, or I'm sorry, in the Wang apparatus, the measurement is 2 stationary devices. There's no relative motion between them. So the theory can't predict any fringe. So he introduces gamma, right? He introduces link contraction and time dilation, and then he sets the value to 1. Anything times 1 is itself, it's not doing anything. So he only sets it to swoop up lab time and lab distance. All right, so we're going to see a trend continue of this. Right now, what's the issue with this? Well, remember, our boy said we're not going to assign velocity vectors to a point in empty space where electromagnetic processes took place. Okay. So what's the big deal here then? Well, what's the next explanation going to be? Well, here we have Tartaglia in 2015, and this is one of the most cited papers that tries to give an explanation to the Sagnac effect for relativity. Were you going to ask something, Peter?
No, my hot micing. Apologize.
No, you're good. I thought I heard you breathing, but I was trying to hit some water anyway, so took a little break.
Yeah, sorry, I'll stop there for a sec. Does anyone else want to jump in or have a comment?
Yeah, if anyone has any questions, by all means, hit me up.
Otherwise, I can start asking questions to direct the discussion, but I want to give other people an opportunity first.
Mord 1's been building.
Dude, Mord 1 is the final relativist boss or whatever. All the other ones have faded into obscurity or whatever. All right, so
yeah, they got too close to the vanishing zone, and they got compressed asymmetrically towards the horizon.
Yes. All right, so let's see.
Did someone?
Go ahead.
Sorry, was someone trying to jump in there? I thought I heard someone open their mic.
Yes, I wanted to ask, in your example, the interferometer rotating relative to an inertial frame, or is it stationary?
Which one? You talking about the Sagnac?
Yes.
The Sagnac's rotating relative to the lab frame, which I consider stationary.
What's the lab frame?
Just anywhere on Earth that the experiment's being conducted is the lab frame.
Okay. So it is rotating. In that case, it would be non-inertial.
According to what?
Well, according to your own standards, you consider the lab frame as absolutely stationary, so everything that would be accelerating relative to it would be non-inertial.
Lab frame is stationary. The rotating interferometer and or uniformly moving interferometer in a straight line is moving relative to the lab frame.
It's
So-
rotating. It's not moving in a straight line.
Well, at a uniform constant speed, Einstein says you can treat that
Angular
the
speed.
same. Doesn't matter.
No, he didn't. He never said that.
Okay, well, we can read the quote real quick before we continue. So this is
Back to that
from
quote.
so this is from section 4. The physical meaning of the equation obtained in respect to a moving rigid body and moving clock. So this is clocks A and B around the equator. Clock B is stationary at the equator. Clock A moves around the equator. It is at once apparent that the results hold good of this coefficient of 1/2 times t times v squared over c squared. Holds good if the clock moves from A to B in any polygonal line and where points A and B coincide. If we assume that the results proved for any polygonal line is also valid for a continuously curved line, we arrive at the results. If one continuously circular blah, 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 he goes on to say that that's where they apply.
He's describing rotating paths there, right?
He's describing a frame in which an observer and a light source are fixed, but they're rotating at a constant speed.
Yeah, so rotating compared to an inertial reference.
Mm-hmm. Sure.
In the maths, these numbers drop out from integrating the path, whether it's polygonal or simple.
Oh, indeed. And
Circular.
if the relativistic effects drop off, all we're left with is the classic. Because what we're left with here is in the moving frame, we have an agreement with a measurement that's being made with what we can see in the lab frame. So we have two timelines that shouldn't be connected if we're going to give Einstein the benefit of the doubt here on how we should treat time and it being locally defined between coordinate systems and not absolute in regards to all of that. So we shouldn't, at the very least, if we're in the lab looking at this apparatus, we shouldn't be measuring a fringe difference. But yet both of them comport, and that's why these lads, well, that's why everyone does a little tricky trick where they borrow absolute time and space from the lab via transformation, and then they drop the relativistic terms. And that's exactly what we're going to see from our boy Tartaglia here, who starts off by saying, hey, we're going to invoke a fictitious midpoint, and we're going to call it L2. And this interferometer is going to be moving relative to this fixed midpoint here for symmetry. And then we're going to introduce our gamma factor, right? But then check out what he does at the back end here. So we're hella gamming out through all of this, right? Some of this is kind of small. You can't really see it, but it's basically a lot of gammas, a lot of transformations to describe the clockwise and counterclockwise configurations with respect to this, I'm using air quotes, arbitrary midpoint that was injected. It's not arbitrary, guys. And then what we're left with down here is that the delta t, the change in time with respect to clockwise and counterclockwise, is going to be 8 gamma plus a, or times a plus b over c times beta. And this is asymptotically equal to 2 over length times velocity over c squared, which is the classic Sagnac formula. Now, this is not asymptotically equal because if you expand this series out, the gamma factor will never equal the first order fringe pattern. That's insane. He only dropped out the gamma factor here because he already borrowed lab time and space. And the only way to have a measurable deviation in the first order difference is to then use the comparison with the classic formula.
That is a trick.
So did Tartaglia and the boys explain the Sagnac effect and Wang's experiment and in terms of a relativistic treatment? Absolutely not. And one of the first things they say in their paper, which I don't have highlighted though, was that, you know, they go over the classic treatment and how it's C plus or minus V with respect to clockwise and counterclockwise, and how, you know, they're going to give it a relativistic treatment. Well, their treatment was to do a trick essentially. And then we'll take a look here. Oh yeah, so here's a bigger so you guys can see it. So they have this series here where presumably you would expand this out and you would get the equivalence of the classic equation, which is on the right-hand side there, which is not what happens. All right. So we can go over to, so here we have Tartiglia trying to explain an experiment. So this is a crazy one. Check this one out, lads. 1 second. I got to pull up the, presentations. Optics. No, it's not optics. Aether, maybe. Oh, nope, that's it right there. All right. All right, 1 second. We just got to wait for Canva to load up, boys. And then we'll go over this really cool interferometer experiment with a with 45-degree angled mirrors. All right, well, we will come back to that in a minute. But anyway, I'll just describe the premise and we'll go over here in a second. So anyway, there's a source and a detector fixed to the lab wall, right? Just bolted to the lab. And they're shooting, the beam is being sent to through a collimator and then to a beam splitter on a uniformly rotating platform that has 45-degree angled mirrors. So the beam splitter sends light around a circuit that hits 45-degree angled mirrors. Those hit a bottom plate that's stationary. I'm sorry. The plate on top is stationary. The bottom plate is rotating. The 45-degree angled mirrors get split to the bottom, and then the rotating portion is rotating out from underneath it with 45-degree angled mirrors. So it completes a circuit on the bottom rotating portion, and then it gets sent back up at when the 45-degree angled mirrors line up. And they also had a configuration such that an apparatus that there was a detector on the rotating portion too on the rim, so that they could take a comparison to see what the rotating observer would measure on the rim versus what the LAD and the lab measures. Because remember, if we're going to use relativity theory, inertial LADs measure the speed of light as being c, so they should definitely at least predict no fringe. And then we'll see what the rotating apparatus predicts. Let me see if this is loaded up yet. There we go. Perfect. Okay, cool. So here's a little diagram, of their apparatus. So we have the lab wall back here. We have our light beam coming in, hitting H. H is our beam splitter. You can think of it like that. And we got a beam going clockwise and counterclockwise at these mirrors that are 45 degrees. They hit mirrors that are also 45. They traverse a little path on the table. One of them leads to a beam, half silvered mirror that will recombine them to hit another detector. And then another one, because it's half silvered, it'll split, or, it'll allow it to go through and continue, and then traverse the rest of the circuit and go back to the 45-degree angled mirror. So when these line up, the circuit is complete, and then we can measure the fringe difference here. So what we're looking for here is, can we measure the rotation rate of this table using two observers where they're fixed to the lab wall, where there's absolutely no relative motion between them? So this is a screenshot of the apparatus here. It's kind of hard to see, but this is the top bit, stationary. This is the bottom bit. They were separated by about 10 centimeters. And so this is just a little highlight of the light path here for clockwise and counterclockwise to show what that looks like there. This is the classic Sagnac formula. So what we were looking at earlier with the, 2 times V over C squared or whatever. These are all the same equivalents here. The higher order term drops out. It's always proportional to V over C if you're much slower than the speed of light, etc. So see, we'll continue moving on here. So we're gonna look at the fringe pattern measured here on the lab wall and on the rotating turntable. They both measure the exact same thing. And then so this leads to the problem here where relativity theory predicting that this, they should measure no fringe. Well, a man named Paul Langevin had to come in, a Frenchman, and give them the the general relativity solution for it, and kind of explain what was happening here, because the relativistic theory is off by a factor of 10 when you try to predict the fringe difference by properly applying it to the frames where the measurement is made and where the source is, without invoking a fictitious midpoint. It's the only way Paul Langevin was able to resolve this was to use the fictitious midpoint that we talked about, that was, that we're not supposed to be able to use. Yes.
What makes it fictitious in your view?
That makes it fictitious is that there is no observer there. And the fact that the classic theory, right, you need a fixed point for the motion to be relative to, and relativity theory, all motion is relative to some other thing that's in motion. There's no fixed absolute rest frame or anything like that. And if that's true, then you have to like analyze it with respect to how the experiment was conducted in those frames. So you have to analyze it through the source and the observer. They actually have a term for it. It's relativity.
What happens if you don't do that?
Then you're violating the principles.
Yeah, but according to your interpretation, but
according to Einstein. It says it right here.
Sure about that.
On the first
I'm not
page.
sure about that.
What do you think this part means?
Let's see. This is kind of been being I can't actually see your screen that well. Am I the only one that it's fuzzy for?
I can make it a little bigger. Does that help?
No, it's like not focused.
Oh, really?
Yeah. Alan. Yeah.
Yeah.
Oh, okay. One second.
Yeah, I don't know what's going on there.
Change quality.
Might have just been on my side then. Sorry.
No, you're good. How is it now? I had it on 1080p. It might have been too high.
No, it's way better.
Good. Oh, okay. I'm sorry.
Yeah.
Shoot. You should have said something. Was it like that the whole time?
Yeah.
Oh my apologies, lads. So sorry about that.
Good.
Yeah, no worries. It's good now. It was fine.
Okay. Yeah. So remember the classic theory, which his mathematical framework is based on, right? He's saying he's proposing a different thing. So what do you think he's saying here with like this right here?
Let's see. The introduction of aluminum if there's ether will prove to be superfluous, inasmuch as the view here will not require an absolutely stationary space, aka the Lorentz rigid ether, nor assign a velocity vector to a point of the empty space in which electromagnetic processes take place. What he's saying there is that the ether as a concept is not required because no fixed absolute reference frame is required. And he's specifically most likely referring to the theory as posed by Lorentz, who was trying to save the ether. And you sort of rightly posed that Einstein's theory can be thought of as a modification to Lorentz's theory. But I think the critical thing that he's saying here, and the whole point of these two sentences, is that you don't need the ether. Because that
you don't need it as a physical substrate or mathematical, right? Because the important part here is assigning velocity vectors to a point in empty space in which electromagnetic processes took place. So not only is he removing it as a physical substrate, also a mathematical concept, and then through relative simultaneity, he removes it philosophically. Wait. Yeah, go ahead.
So I can't really. I'm not a like a relativity guy. I can't speak specifically towards what he means by assign a velocity vector to a point of the empty space, but I think that's just referring again to the nature of what the ether would be. Like, I don't think that it's actually making a statement that's. I'm not sure that it's saying exactly what you think it says there. I don't think the meaning is completely clear there without some additional context from the physics. Like, from what I'm reading. But.
Right. So, well, let's break it down. So it says, inasmuch as the view here to be developed will not require an absolutely stationary space, so no rigid ether, like you said, right? Like mechanistically, right? Provided with special properties. Like one of those properties would be, being able to measure motion relative to it, right? You could consider that a special property, I suppose.
Could you?
And yeah, sure. I think it would be an inherent property, but that's what he's saying. Because the whole premise here, leading up to the explanation to this, here he's talking about all the experiments where they tried to measure the relative motion of Earth to the light medium, gave a quote unquote null. So from that, he's saying that, there is no static medium here. And then he says, see this comma here?
That's not what he's saying.
What?
That's not what he's saying. He's saying He's not saying that there isn't one. He's saying that it's superfluous. He's saying that it's not necessary for the theory. He's not really making a statement of the non-existence of an ether here. He's just stating that it's superfluous
So
insofar as the reason the ether was useful in classical electrodynamics prior to Einstein and prior to Michelson-Morley was that the notion of absolutely stationary space depended on that ether to make reference to. And that's the whole reason that the two hypotheses you cited from Michelson-Morley with respect to Fresnel theory of the ether are important, because it's a reference. So all he's saying here is that reference is not required. He's not making a statement that
right. Okay.
something called the ether doesn't exist, as far as I can read.
So check this out. He's explicitly saying that, because if it doesn't, right, and if it's not superfluous, like if it's something that's needed, then you're going to have to explain why Michelson-Morley didn't have a fringe difference. So the purpose here, no.
But it's not.
One second, Mort. This is the premise behind it, right? It's not just superfluous. He's saying that you don't even need to think of it because it doesn't exist. Because
no, he's not saying that.
Okay, well, one second.
You're adding but hold on, you're adding meaning to the sentence that isn't there.
The theory here will not require an absolutely stationary space, bro.
Will not require. It doesn't say it obviates that like the entire point of this sentence, as you're stating it, and maybe I'm being pedantic here, is that he's simply stating that the ether is superfluous. It's not needed because relativity obviates the need for an absolutely stationary reference frame or an absolute reference frame of any kind. But that doesn't necessitate that the ether itself doesn't exist.
It can't supersede the classic theory unless it can replace it and give an explanation as to why there's no velocity difference. Because the important part here, right, if you're in a fluid medium, all motion is going to be relative to that medium. So he's literally decapitating it right here. It's like this require an absolutely stationary space for the motion to be relative to, provided with special properties, nor are we going to assign velocity vectors to a point of empty space in which electromagnetic processes took place. So this is the mathematical treatment that's going to be given here. And this is the whole purpose of saying this is how everything is going to be treated moving forward using Lorentz physics.
Right, but the Lorentz physics predates Einstein, and Lorentz physics itself is modified by Einstein in this paper to obviate the need for a medium which Lorentz was trying to preserve.
Well,
so
I
just don't see
what does obviate mean? Like what do you mean by obviate? Because you can't you can't say. So let me explain the difference here. If there's an ether mechanistically and mathematically, then you can't then time and space are absolute, and he's not saying anything different. So the whole point, because this framework, as you pointed out, comes from Lorentz, which comes from Voigt, which is a theory of timing and spacing of waves based on an elastic medium. So the whole link contraction and time dilation, things changing as a function of velocity, is facilitated explicitly by a medium that would facilitate motion being relative to it. This is why he has to remove it.
Why are mediums in the sense of an ether? Why can you not have a version of relativity in which an ether exists?
Well, because all motion would be relative to it. So think about this. If you're in a pool,
what if it wasn't?
Well, that doesn't make any sense. That's logically incoherent.
Says you.
That's why, well, think about it. If you're in a pool, right? How do you measure distance and velocity? You can use sonar, right? So you can use a range measurement equation. So you would use the speed of sound in the medium, and from that, your relative motion in that medium, you would measure the speed of the wave plus or minus your velocity. You would never say that the speed of the wave is a constant, but the only way that you could do that is by saying that you're not in a pool.
Right.
No, because I've seen modern incorporations of the notion of ether into space-time physics. So I just don't see that this in and of itself. I'll leave it there, but I'm not trying to push you too hard on it. I just don't see that you're good. Respectfully, what's read here says what you think it says. That's all I'm trying to say.
No, you're good. And this is a really good point to bring up, because people try to introduce ether theories into them, but they always get rejected. And the reason for that is because you can't have relative distances, you can't have relative times, you can't have relativity of simultaneity if there's an all-pervasive medium that everything is relative to, so that it fundamentally undermines the theory. Now, here's what Einstein said in the 1920s on a book called Relativity, the General and Special Theory for the Layman, or something like that. But what he says was that
can I ask you one question, though?
Go ahead.
You seem to put a lot in the statements of Einstein. And I'm curious if you also put stock in the statement that the motion of the Earth around the sun can just as easily be explained as, the classic one, right?
Yeah. Yeah. And I'm telling you why, and I'm helping you explain why he thought that.
Right. But my point is, do you accept that statement is true, that the notion of kinematic equivalence in orbital mechanics is true?
Yeah.
Okay. So that by itself, the reason that Einstein made that statement was on the basis of relativity. That equivalence only exists in the framework of relativity.
Well,
so I see a problem here, because if you accept that one aspect of relativity, and it is general relativity, it doesn't work with Galilean relativity, then you have a problem here, because it's in conflict with your rejection of relativity on these grounds. And I get your criticism here, but I don't see first of all, I don't think that going off of just like an interpretation of what Einstein said is always the best. Secondly, doing so in relation to kinematic equivalence requires an assumption, and most of the things Einstein said require, that are sort of famous quotes of him, require the assumed premises of general relativity to be true.
Well, you got to understand here, he's not talking kinematics. He's giving a dynamic explanation. He's saying time and space are physically different. That's a primary distinction to be made here, especially for the general theory. The kinematic equivalence of the frames is for frame equivalence. That's a kinematic postulate. He's trying to assert dynamics here. And
yeah, but the whole kinematic equivalence is based on general relativity. You don't get kinematic equivalence in orbital mechanics without general relativity. That's my point.
Kinematic equivalence has nothing to do with general relativity. There's Kepler's laws. All you're doing is watching something, and it's a ratio of a periodicity. It has nothing to do with relativity theory. It's a ratio of pi to periodicity.
We'll table that for now, but continue.
Yeah. Okay. See, there was some other thing you said that, anyway, we'll keep going. What's that?
Paul Langevin? I think that's where you were.
Yeah,
at.
well, I just want to say Paul Langevin, he's a Frenchman, so nothing good ever came out of France. So
That's true.
I think we should.
That's true. All right, so back to Langevin. Oh yeah. We were on this right here in the general theory, trying to explain it or whatever, right? So he says, hey, I got to get my fictitious midpoint here to describe the relative motion, and without that, I'm cooked. So now we can look at what his treatment for that was, and what he does is he just borrows the time coordinate from the lab, and then he binds it to this section over here, which is basically making the speed of light dependent on this angle relative to the radius. And so like this central time here that he's using, right? He's just using lab time. And then just constructed this entire coordinate system using absolute time and space. And then he's just saying C plus or minus V to the first order approximation with respect to the rotation. So he created a scenario in which you can have directionally dependent speeds of light, clockwise and counterclockwise, with respect to inertial observers. That is not what the theory predicts, right? This is a mathematical treatment that violates this section right here, nor assign a velocity vector to a point of empty space in which electromagnetic processes took place, which is exactly what old Langevin has to do after, of course, borrowing time from our friend, the lab. He also gives a second explanation where he ties coordinate time to the rotation fixed from the radius, or away from the radius, and then now coordinate time changes with respect to rotation, which ends up giving the anisotropic speed of light, clockwise and counterclockwise. But this effect isn't measured as an effect of coordinate time transformations. It's an effect due to rotation, right? Due to real actual motion, not a theoretical transformation. So, and also borrowing lab time again. So none of these are giving an actual treatment so far, but they're presented as, giving an explanation to it. But the important distinction here, like relying on, why is it important to go with what Einstein's saying here? Because this theory by itself is also an ether theory. So we need to understand what the context of what he's modifying about it is. All right. So that was Langevin. And as Morty said, nothing good comes from the French unless it's Sagnac. All right, then we have Dr. Blitz trying to do the same thing here, where he starts with a Minkowski coordinate system, borrowing lab time, ends up doing the same thing, c plus or minus v, with respect to the direction of the rotation. There is no way to give a relativistic treatment to this, because if a light beam is split and the observers are inertial, and we're not assigning velocity vectors to preserve the change in distance for the movement of the apparatus, then the speed of light will traverse the distance and complete it at the same time, leading to no fringe. Google. We have a quick look at this real quick. Relativity. What am I looking for? Relativity debate sources. Engelhardt. All right, classic and relativity derivation. So the whole issue here, right, is trying to interpret this measurement in the actual context of relativity. This is what makes people become not relativist, when they realize that this can't be done, and they've been doing classical physics masquerading as relativistic physics, doing things up to and including introducing a continuous flow of time called a killing vector field, and then doing differential calculus off of absolute time created by the introduction of that to describe that within a manifold, but like still violating the core principle. Like none of these things, there should be a coherent explanation to it, yet we're seeing, just an utter use of classical physics disguised as a relativistic formalism. So here's the classical treatment here, where we have the clockwise and counterclockwise rotation and the length being preserved with respect to the lab frame. So we have the timing difference as the mirrors move away from the apparatus, and the quadratic term here is too small. It cancels out. So you remember our boy gamma factor, link contraction time dilation? Yeah, not a applicable term. We're only concerned with this. This reduces down to 4 times the area times the rotation rate over the speed of light times the wavelength, and that will give you the predicted change in wavelength as a ratio of the area that light had to travel and the rotation rate. Very simple and easy. So what we do for the relativistic prediction, right, for inertial observers, speed of light constant, no preservation of the path length change, well, then the timing difference is going to be equal. It's going to be no length change. It's going to equal 0. Length change with respect to C is 0. Pretty straightforward. And then again, they talk about how this was, from Voigt from 1887. But anyway, any questions, comments, or concerns on old Sagnac and the boys?
No, I think thanks so much for dropping in. I think as far as like from our side, we'll kind of wrap the event up here, unless there's any like major points that weren't covered that you wanted to cover. Thanks for the back and forth as always. And yeah, unless there's any general discussion as well, because people are here, we could open up to that as well. So good to see everyone here. Thanks for dropping in, Aether Cosmology crew, and Austin as well. So thanks.
Yep, there is a mildly important point to bring up real quick. So earlier, before we began the discussion, neutrons were brought up, and how neutrons are affected by gravity, did you also know that you could measure quote unquote sidereal rotate? Well, you guys would call it Earth rotation, but you could measure sidereal rotation with neutrons. There's a neutron interferometer. Definitely check that out. So neutrons obey the Sagnac effect, which I think is some sort of medium facilitating that mechanism. And then obviously electrons do the same. So we have all these, quote unquote, subatomic particles, quantum materials obeying sidereal time. Very interesting and cool stuff.
Except in space.
What's that?
Well, by sidereal time, you're admitting the rotation of the globe, right?
Well, that's kinematics, right? So we have a motion of measurement. Does it mean that the Earth is moving, or does it mean that the sky is moving?
Rob also wanted to get in, so
go ahead. Oh, sorry. 1 second. I have to turn Rob up. Go ahead, Rob. Start over, please.
Sorry, Alan. I don't know if
No,
it's.
you're good. You're good. I had you turned down.
Okay. I just was hoping. I'm not sure about this Aether cosmology thing. Is there somewhere that I could learn more about this?
Absolutely. On the YouTube channel, space_audits, on the YouTube channel, Shane St. Pierre, or if you go to spaceaudits.net, I have an Obsidian page where I have a bunch of research. I'll actually link it in the text chat here for you.
You guys also have a Discord?
We do.
Is it possible that you could send me a Discord invite, please?
What is your name? Because I had your volume turned down to 0. Rob who?
Rob Keane on the level.
On the level.
It might just say Rob Keane. Hang on, I'm in the screen share.
All right, we'll get you in. We'll get you squared away here in a minute. But yeah, here's a link. Here's a link to
it's just Rob Keane.
Here's a link to the database there. You can go down to the presentation section. There's a history of interferometry. There's a ether physics prezzies, all kinds of stuff on that.
Thanks a lot. That's all.
Mm-hmm.
You can go back to Shoe Bill. That obviously didn't hear me say I had a question.
Oh, no worries. What up, Shoe Bill? Did you have something else you wanted to add, Shoe?
No, it was just sidereal rotation is Earth globe oriented. I didn't know what your position on that was.
Oh yeah, so my position is that the measurement alone can't differentiate between ball rotate and sky rotate. We'd have to introduce some additional variables. Now there have been some experiments that were done at altitude, and I'm not even counting Bob's experiment, right? We can completely throw that one away. I can reference a couple of other ones that were done at altitude that give it a variation, which to me which means like that the speed increases, which to me indicates that the source of the rotation is the sky essentially.
So that would explain the difference in a reference mass weighing different by latitude.
Yeah, so you could get into different mechanisms for the cause of gravity, right? Like, so if you wanted to go the electric static route, I mean, I wouldn't say.
Well, this is centrifugal. No, that's centrifugal force.
Well, 1 second. I wouldn't say that latitude-dependent gravitational effects are model-specific if we don't understand the causal mechanism of gravity truly. And if you were to invoke gravity as like the causal mechanism, which I'm sure you would be comfortable doing, I would say that, Big G, the cosmological Big G, has been falsified by Michelson-Morley and other experiments as well. So in other words, the causal mechanism is in contention, and latitude-dependent deviations in gravitational potential wouldn't be mutually exclusive.
So sidereal time is the stars rotating.
Yes.
So all the stars rotate in concert, so they must be at the same distance?
Well, for navigational purposes, that's actually how they're treated at a celestial sphere where they're all equidistant from one another, rotating. So, I mean, for all intents and purposes, you can certainly treat it that way.
But observationally, they do rotate in concert, and we know they're at different distances.
Do you not know the difference in angular speed and tangential speed?
Well, you say different distances, right? But that's like doing trigonometric functions, making different assumptions. So if you were to assert parallax, for example, or stellar parallax, right? That would be under the assumption that the Earth is 93 million miles away from the Earth and then sun, and then 6 months out of the year, it's going to traverse about 186 million miles or whatever to complete the baseline of the triangle. But if that were true, then Michelson-Morley would have measured 30 kilometers a second. So that's where I'm saying that like Big G is in contention in that regard cosmologically.
Well, Michelson-Morley would have measured that if they were passing through an ether.
Well, they measured 6 kilometers a second. So the way that I interpret the measurement is that the Earth is stationary and there's a dynamic ether that translates the motion of the position of the stars and the sun as well, because there was continued experiments that were done that show a minimum and maximum dimension on the fringe patterns, meaning the speed of light reaches its maximum and slowest speeds on the equinoxes. And that was done by like 30 years of experiments from a guy named Dayton Miller and corroborated in more modern times by a few other people. It's just not to the magnitude that heliocentrism requires. And because it's an interferometer and because of the relationship with the fringe pattern and the square, the distance being proportional to the velocity that produced it, they can't acknowledge it. They have to like say that it's experimental error, etc. But I take it as is.
Why'd you ignore when Alan said that it was different relative to altitude?
Oh, just one sec, real quick here, guys. We can continue the back and forth, but Melodic requested jumping in to the voice queue. So
nice.
Unless
Welcome.
Shubo has a response, to what Witsit just said, we could turn it over to the next speaker. But go ahead if anyone else has a response to that.
I pass.
Alan, how do you respond to the study by Chiba et al. From March about pulling an electromotive force from the Earth's axiosymmetric magnetic field?
Ooh, can you send me a link to that? I heard.
It sounded like whatever,
in fact.
Whatever physics you were describing just fucked your mic up. So I'm sorry, go ahead.
You got lost in the Coriolis.
Because the Earth rotates, they're able to pull energy from the magnetic field.
Interesting.
Because when you rotate a magnet, the magnetic field does not rotate with the magnet.
Right. So mechanistically, we would have to get into introducing some different variables there to distinguish, like the cause. Is there a increase in altitude, etc., sort of thing? Is it latitude dependent? But one of the most.
So they moved it.
One second. You're kind of lagging out super hard.
Yeah, Melodic, you have some serious mic issues going on.
All right. Well, let me move into here then.
Yeah,
not melodic at all.
So to describe the methods which are in the paper, it's in a room with no windows. There's no lights. They go in. They move it. They leave. They don't even bring in. They bring in phone lights like headlamps to move it. They move it. They let it sit for a night, and then they come back and begin their measurements.
Well, I will take a look at it, but my contention, of course, would be that that's kinematics. We would have to introduce some additional variables to tell which is actually in motion and what the causal mechanism truly is.
It's not kinematics.
It's literally
not kinematics.
It's a measurement, right?
It's not kinematics.
Did you say that?
I would challenge you to actually open the file and look at the equations being used before you say that.
Measurement of motion is kinematics.
No, it's not. Witsit.
All right. Well,
it literally is. By
that's literally just definition, bro.
It is not. Witsit.
Okay, can you define kinematics?
No, Witsit, I'm not your physics teacher. You should have learned stuff while you were in Antarctica.
Okay. 1 second here. 1 second. We're not here to be like, fake hide things. So real quick, we're gonna detract before we come back to Robert. What was this? Thomas Roberts trying to refute Miller here. We'll come back to that, but we're going to get the definition of kinematics and dynamies real quick for the boys.
That'd be great.
All right.
Measurement of motion.
Kinematics and dynamics. Okay. So here we have Shankar, one of the most popular physics books known to the lads here. So we have the Newtonian procedure for predicting the future given the present has 2 parts. Kinematics and dynamies. Kinematics is a complete description of the present. It is a list of what you know about the system right now. For example, if you're talking about a piece of chalk, you want to know how fast it's moving. Dynamics tells us how and why the chalk goes up and down and so on. It comes down due to force of gravity. In kinematics, you don't ask the reason behind anything. You simply describe things the way they are. In dynamics, it tells you the description of why things changes with time. So the variables that are going to be in the equations when I look at them are going to be, let me guess, sidereal time for rotation, right? And the measure. Okay, then what do you?
Nope.
Okay.
Again, if you're going to talk to me about the equations in the paper, I would challenge you to open the paper first.
Fair enough. I will take a look at it then. If it doesn't start with that, then I will take a look at it then. All right.
All I know is this guy just said
but real quick.
Again, it's not a measurement. It's not a measurement of motion. Once again, it is pulling EMF from the magnetic field. The fact that it does that happens to be secondary to the motion, but it's not a measure of motion, so it is not kinematics.
Yeah, you're a
I'm not asserting. I read the paper and I know. So stop trying to tell me what I know about a paper that I.
My good sir.
Hey, control. Okay.
Yeah, let's take it down a notch, guys.
Yeah. All right.
Okay. Well, what's the plural use of the word guys there? It's clearly one guy. Wow.
So to be clear though, right? The measurement could be produced from Earth rotating or ether rotating. We would have to do additional things to determine which is true. So that's why I say it's kinematics to begin with, right? So I will take a look at it. If you tag me with the paper, I will take a Gandy. Now, we can get back to, now that we've defined kinematics for everyone, we can get back to ether. Go ahead.
Melodic, just hang on a second. Let him finish.
Oh, I thought he was done because he asked me to link something,
Okay.
Jeez, dude, chill for a second.
Jeez, Whitsitt, shut up for a second.
No, boys, let's not. It's all
wasn't
good.
even him.
It's all good. It's all good. We're in a ceasefire, boys. It's all good.
Fight.
Yeah, just.
You don't need to be so aggressive, bro.
All right.
Yeah.
So while we're doing that, we will look at, thank you, sir. I will get this down in my Zotero real quick.
Yo, Alan, you defeated the final boss, Mordwan.
Morty Moore?
You are awarded top Flat Earth Defender, and Whitsitt, I demote you to the new Haktua Girl is your new title.
New Haktua Girl. What is that?
I don't know what that means. Is that good or bad? I don't know.
It depends.
The optical engineering vein of the honeycomb stacking lattices.
You
Is
just
that
say
it?
devoted, yeah.
Experiment? No, that's not it. Okay. Well, I'll come back and get that later then. But thank you, sir.
You're ace in my books. Don't worry about what they say.
All right, lads. So earlier I mentioned Dayton
It's
Miller.
so gay that you're making that sound about a girl sucking the dude's dick. What's wrong with you?
Oh,
I'm just
yo,
making fun of you for spitting on girls.
yo, boys, we're having a conversation about physics and cosmology. What you're doing is a complete distraction.
Yeah, Quap, don't do that.
Sorry, I server muted him. Let's not do
okay.
personal attacks, please.
Yeah, no worries. So to move on here, we have we talked about Dayton Miller earlier and how the measurements of interferometry in the east-west directions correspond to sidereal time and how they also correspond to the position of the sun. And then so this guy, Thomas Roberts, comes through with a Fourier analysis saying that he, under his analysis, he found that there was an error that Miller measured, that this was a mistake. Let's take a look here at what he does. So posthumously, Miller is now experiencing every experimenter's nightmare. The standard analysis algorithm used by himself and his contemporaries has a serious flaw, not explicable for many decades, and it caused the noise of the apparatus to perfectly mimic the real signature. What kind of assertion? Like, just think about this for a second. This man built multiple interferometers, like not just one, right? He had multiple, some for control, some for different control, like temperature, different materials, etc. right? He keeps measuring sidereal fluctuations for 30 years. And this man says that the noise is perfectly mimicking a real signal. So how does he conduct his analysis? Well, he sets the error bar to the noise and then removes it with his Fourier transformation and concludes that there's no real signal there because he removed the signal. And he doesn't show his math. He doesn't get into anything like that. There's nothing in here to substantiate any of that as it continues on. This is what he just asserts that it just mimicked it. Now, if this were true and this was just a mimic, then the experiments couldn't have been replicated. And they were replicated by at least two other people that I can think of off the top of my head. It was Hector Manera in 2002 and Yuri Galev in about 2003 or 4. In different locations, different altitudes, etc. And actually, Hector Manera left his apparatus running for 3 years straight. That's a pretty, they have all kinds of data for that. And they measured the same minimum and maximum fluctuations in the speed of light. All right. Does anyone have any questions or open discussion stuff? If not, we can kind of wrap up. I know relativity is kind of a dense subject. I know it's not everyone's faves. These people are probably getting antsy, and I respect everyone's time here. Thank you guys for listening to all this.
A quick one.
Yes.
Oh, sorry. So tools that use Sagnac-like effects like ring laser gyros and things like that,
yes.
Would you expect them to still function as predicted in spacecraft and in orbit and be useful in those scenarios?
So that's really interesting. So have you heard of the, I think it's the Go Fast rocket or one of those like Go launches or whatever. When we were looking at the data from them, because it was asserted that, it was too high or what, I can't remember the assertion, but anyway, we were trying to figure out the altitude of it, right? Essentially. And they said that at a certain altitude, their GPS stuff doesn't work, and they had to get special permission to get a GPS that would go over a certain altitude because of national security reasons. And then their inertial navigation systems stopped working, so the gyros and all of that. And they were trying to send up radio signals to like bounce up back and forth to like take differentials, and that wasn't working. And they ended up based on all the discrepancies where things stopped working, which I forget the altitude, but they ended up with like a 16-mile difference in like where the rocket could have been or whatever. But I would expect it to work unless there was some ether related reason as to why it wasn't.
Yeah, because they're certainly in attitude control
Mhm.
satellites and stuff like that, or spacecraft. I guess orbiting satellites attitude control is a bit different, but certainly in spacecraft, they ring laser gyros are very prominent. Back to the Go Fast rocket, some guys in New Zealand just did a 120-mile shot
Ooh,
from New
nice.
Zealand, and they had GPS that functioned all the way.
Ooh.
Yeah,
Cool.
the rocket you described that lost comms or got lost because of GPS or gyros, was that anomalous, or is that like all rockets, but maybe
No,
you're just picking out this one?
No, I think it was a couple of the private ones, because we were looking at because we ended up doing like a comparison, and like this other team had the same problem, so it seemed to be maybe like localized commercially. Like I'm not sure, but that's where I.
So percentage-wise, by the number of amateur rockets or Go Fast rockets or sounding rockets, percentage-wise, this is not common at all.
I don't know. It could be. I mean, it could not be. I don't know. I was literally just offering my experience. He said, "Do you expect it to work?" My answer is yes, and then I provided a scenario that I looked into where it didn't. Like I don't know. I would expect it to work.
As it does most of the time.
And the other thing I was going to ask is it's not directly related to the Sagnac stuff, but we were talking about the kinematics and dynamics of the solar system, and Kepler's equations. I think we've had this conversation before that we need more than Kepler's laws to describe the motion of the bodies in the solar system. They're simply not adequate. They're an okay starting point, but they're not enough. And typically that kind of analysis is done from an inertial frame of reference. So you're going back to the spacecraft trajectory planning and stuff like that. That's all done from an inertial frame. And all of the motion of the bodies, all the other satellites they have to avoid, all calculated in an inertial frame of reference.
Oh, it's my premise that all predictions of future motion are done with respect to an inertial frame.
It's like Earth is stationary or something.
Oh no, Earth is moving within that inertial frame.
I mean, it's been asserted
Earth
that
is not inertial. Yeah.
I mean, that's the contention, but it only seems to be when light is being used to measure that assertion can be made. That's where it falls into my domain.
So one of the best inertial references, man-made ones, is actually the orbit of a satellite, right? That plane there is highly stable inertially. And that clearly shows the Earth rotating under that inertial plane. And similarly with something like Sagnac in GPS,
When you say,
don't use it, doesn't work, right?
1 second. When you say it clearly shows it, what do you mean?
So the satellite's orbital plane is fixed relative to the rest of the universe that we can see, right? To that bulk of that inertial matter in the universe, like the galactic. I think that what they call the galactic inertial reference frame or something like that. That is a good best guess at a true, something that's inertial compared to everything. So the satellite orbital plane is stationary or fixed in orientation in that inertial space, and the Earth is clearly rotating relative to that inertial frame.
When you say clearly, like, do you mean like from an observer on the satellite looking at it, watching the Earth?
So from an observer in the inertial frame, the Earth is rotating.
We'll check this out, home dog. For an observer stationary on Earth looking at the satellite's moving around him. So we're at a kinematic. We're back to kinematics.
Yeah, except you can demonstrate that there's non-inertial properties on the surface of the Earth, right?
Say that again.
What?
You can demonstrate on the surface of the Earth that there is non-inertial behavior.
Is there a place on Earth where F doesn't equal ma? Is there a place on Earth where you can fail to make the correct predictions of the laws of motion using Newtonian dynamics?
Yeah. You lob a projectile in the right direction, and you expect it to follow F equals ma, and in particular, the trajectory should follow a particular path, and it doesn't, right? It's Coriolis and Eötvös in that case. And similarly,
so you're saying you have a measurement of someone throwing a baseball and it being off due to Coriolis?
Not a baseball. No, you need
light,
a long range, high mass object to properly measure impact of Coriolis.
Citing a baseball, that's kind of disingenuous, isn't it?
He said throw an object.
I can post a video of somebody. I can post a video of somebody throwing an object in a rotating room, and it shows exactly how Coriolis works, very plainly.
Yeah, but we're talking
and
about the Earth.
If we throw a ball on Earth, does the same effect represented? Cole?
No, it's not representative. It's not, because we have to do it. It's like trying to say you could get your. It sounds like something that Mikey would say about getting your horizontal plumb blobs and it's flat because we've got a horizontal plane here. You know that you need to be able to measure something that's rotating at 15 degrees per hour, right?
So no matter what,
something that's in air for long enough.
No matter what force you're trying to impose to make the correction for the prediction or whatever, right? The prediction itself is fundamentally starting with the lab frame being stationary either way, which is my premise. So you want to say that there's a force acting on it that's going to cause deviation. Well, the only way you're going to predict the correct deviation is with respect to the lab frame, which is my premise. So anyway, like I said, the only way that
Earth, right?
Yes, anywhere on Earth. And so the only way that you can assert that the lab frame is actually non-inertial is through east-west differentials with measurements of light, which again falls under my domain.
No, you can observe it relative to any object that you know will be traveling inertially. So if you launch a projectile, say we've got an ICBM, right? We shot it up, it's out of the atmosphere. Not that you believe that. and it's traveling in space
Mhm.
inertially. It's not influenced by anything other than its inertial motion, right? It's in free fall. The Earth will appear, or it will appear to rotate relative to the Earth, or vice versa, that it will see the Earth rotating underneath it as it travels.
Mhm.
That's evidence that inertial objects and the Earth are not locked together.
That's my premise that kinematically it would be the same. I'm not really sure where you're going with your line of contentioning, Daz.
I'm just saying that the Earth is not an inertial reference.
You just said that kinematically it looks the same from the ICBM, and also like, you know, I,
They both see relative motion that's not one sees the other as being not inertial, effectively.
Yeah.
Right? So from the Earth perspective, you see the deviation of the
They
projectile.
see
But we
they
know
see the same
projectiles
thing,
travel
bro.
inertially, right?
They see the same thing.
No, they don't. No.
Oh.
So the projectile sees the Earth rotating under it.
Hmm.
The Earth looks like the projectile's traveling a curved path.
Mm-hmm. Do you know those are
So-
the same? Like you?
Yeah, but only one of those objects using
Hold
the
on.
laws of physics can have its
Mhm.
path described as an inertial path.
Right, with respect to the old lab frame. So you're not going to make your prediction with respect to something that's moving, right? Unless you're going to treat it as stationary, and in which case it actually is stationary. Otherwise, it makes the wrong prediction. So we're just kind of getting into a hella circular meta argument that isn't really like you're not really differentiating anything from like your premise. Your conclusion's my premise situation. So
if you predict the path of a projectile from an inertial frame, so you create an inertial reference frame, call it your lab frame.
let me save you
and
some time. Just show me a prediction where motion fails to make the correct prediction using the lab frame. Just do that instead. Let's just start from there instead.
Hey, one second, Jesse, were you trying to get in?
Oh, when it's my turn.
Okay, so you'll go.
I was
next.
after Daza.
Okay.
Yeah. So from the lab frame, Alan, you can't predict the path of an ICBM without accounting for non-inertial rotation of the Earth. Either in the form of Coriolis as a fictitious force, or
I don't think
using two.
I don't think you're understanding the situation right. So the motion of the ICBM isn't an inertial frame. You're predicting motion with respect to an inertial frame. Forces that you're imposing on the non-inertial frame to predict its motion with respect to the lab frame is my premise. Sorry, I didn't mean to yell. But Jesse, whenever you're ready, I think.
Yeah. So can I just ask you then, why would the projectile be non-inertial in its motion?
Well, there could be several reasons. The deviation is caused by timing differences in light. So I'm going to guess there's ether wind involved. That would be my assertion. That the timing difference created.
No, right? Newtonian physics. We can do this in the Newtonian space.
Well, check this out, big dog. Check this out, big dog. Mass of the Earth, mass of the ICBM. In the Coriolis equation, the mass cancels out. It becomes centrifugal acceleration. It becomes kinematic anyway. If it even is accounted for, it's in a specific direction, which I'll swoop up as ether wind. No one's ever shown any sort of measurement where we have to account for something deviating, moving perpendicular to the plane of motion on the Earth. So like this, like, whatever, man.
Yeah, ICBM trajectories definitely have to calculate the rotation of the Earth under them. Satellites do. When you're launching satellites, you have to treat the Earth as a rotating reference. You cannot treat it as an inertial reference.
It's actually explicitly done as an inertial reference frame. Like, dude, buddy, okay. Show me predictions of future motion from a non-inertial reference frame. Just do that while we move on to Jesse. Show me the exact paper or reference that in math that you're referencing. Otherwise, what you're saying, bro, is just like show me what you're talking about. Show me the exact specifics.
Okay, I'll dig it up. So all satellite
Thank you.
orbits.
Thank you.
are done.
Thank you. While you're digging it up, though, like we're going to move on to Jesse. I don't need to hear it again. I need to see the actual math now. We've reached our maximum ability to communicate on this circularly.
Before he
All
looks it up, what happens if he looks it up and finds that it is done?
What if
then we'll have something to discuss further.
Yeah.
Well, I mean, doesn't that completely invalidate your point there? Like,
What
if
if,
you have to
bro?
looking this up. No, it's not what if.
Well, when that day comes, we will come to it. Jesse was next with a relevant question, I presume. So we will start with him. Thank you.
And just be fair to Jesse, whoever that is.
I think we lost Jesse. He might have on.
No, I'm here. Just wait my turn.
No, you're good.
Yeah.
I muted that guy. He's not saying anything relevant. Go ahead.
Okay, and this might be off topic, so just say so if it is. But I wasn't sure. Did you say something about the Eötvös effect possibly being caused by static electricity earlier? A lot earlier.
Eötvös effect. Never met her. Is that latitude dependent gravitational differences?
Not specifically. A mass traveling, let's say at the equator eastward, weighs differently than that same mass traveling westward, and so, and it could be, a mass inside a metal Faraday shield hanging on a spring. If it's traveling eastward, it weighs one thing. If it, more or less than its resting weight, and if it's traveling the other way, it weighs differently the other way than its traveling weight, heavier or lighter. And
how did you measure it while it was in motion?
I'm almost done.
That's not an issue. Go ahead.
And then this would also relate to the question of if we had a satellite orbiting around the equator eastward, and then another one orbiting around the equator westward at the same height, if somehow we could keep them from colliding, would they both appear to be going the same speed from an observer on Earth?
Well, if there was an east-west bias differential with the speed of light, the timing differences would reflect the same thing as if the Earth was moving. So it would, based on that bias, no. And the answer to your first question was, could you re-ask it? I kind of forgot it. Sorry about that. I didn't write it down. Oh, it was about it was about the Eötvös. No, I actually haven't even looked into the Eötvös. This is the first time I'm kind of hearing about it with the mass being different in east-west directions. That's crazy, dude. I cannot wait to. What's that?
Yeah,
I've never heard
weight,
that
not the
either.
mass. But yeah, check into it. It was discovered in like the 1800s on a research ship in the ocean. They were measuring the weight of a mass very delicately, and they found it weighed differently when they were going east as compared to when they were going west.
Nice. Well, let's see. That is awesome. So that would still be, I could still swoop that up under ether differentials, but I have to take a look at it. But that's I'd never heard of it.
Now, as for Jesse's question, as a quick follow-up, the a satellite in prograde and a satellite in retrograde orbit at around the equator, as observed from Earth, you said they would appear to be traveling at the same speed. Was that what you affirmed?
No, I said that due to the ether wind differential bias between them, creating the same offset, it would appear that one is going faster than the other. That's why I'm saying kinematics alone can't tell us, right? It's just the measurement.
And then there is the Doppler shift of a signal received from them.
Well, that comes into where we have timing corrections and offsets from the signal being emitted, where, I would have to call into question the ability to make raw measurements and the timing corrections that are on the back end of GPS to make it work. And
No, I was just referring to the Doppler shift of a frequency.
No, I know.
No data modulated on the frequency.
Is it coming from a GPS satellite?
A satellite in prograde and another satellite in retrograde.
Do you think it's emitting signals that aren't already offset?
Yes.
Yeah, they're both emitting the same base frequency. Let's just say it's like 1 gigahertz.
Mhm.
then
speak to that?
there would be a Doppler shift in that carrier wave.
Could I speak to that as a ham radio operator?
Go
Yes,
ahead.
please. I'm out.
So thank you. So there's some satellites that have ham radio repeaters on them, and ham radio operators, I've not done it personally, but people I know have, and many do, can send a signal on one frequency up to the repeater, and it'll transpond it back down on another signal, and so that way two ham radio operators can talk over a much greater distance because they're relaying it off the satellite. The difficulty is, though, because of the velocity of the satellite, they have to tune their receivers up or down in the megahertz or whatever to compensate for that. And at the same moment in time, there'll be one person, with the satellite going away from them, and they have to tune their frequency one way. And the same signal, though, being received by someone who's being approached by the satellite, has to tune their frequency up rather than down. So it's the same signal, but it's arriving at the receivers at different frequencies simultaneously.
Okay.
So they can actually
Let's see here.
tell what the approach or recede speed is relative to their locations.
Okay. So on the back end of GPS, before it even admits anything that you're using to determine whatever, right? There are timing corrections that are made every time they call them meridian corrections. So what they're doing is they're sending. Yeah.
Why GPS? He was talking about a repeater, and we're talking about any satellite, not GPS. Why do you bring GPS and timing data modulated on the signal? We're just talking about carrier wave.
Was he not just talking about a signal emitted from GPS?
No, he wasn't. Weren't you
So
listening?
he was just talking about the speed of the satellite causing a Doppler frequency shift.
Right.
Is that not what he was saying? Shoebill?
Yeah, that's what he was saying.
Okay, buddy. Then that's what we're talking about now. So the signal coming from the satellite, based off of its velocity.
Alan.
Sorry, dude. Sorry, I cannot stand that. This man just. Are you paying attention, Shoebill? So anyway, the satellites, the thing that's emitting the signal, is already corrected on the back end when it passes meridians. So that timing is removed from it, which is essentially changing the position of it. So that when the signal is sent, when it's doing trilateration, it all references back to the specific points that it's supposed to for the coordinate system that it's in use. So when it's referencing the GSW 84, whatever it is, 86, all that, that is what the measurements are comported to on the back end for GPS before it even emits anything. So with that, I wouldn't be able to say like, okay, like your signal is like a raw measurement and let's not correct you. Like, you know what I mean? I wouldn't be able to verify that. Like, I don't accept that as a raw measurement.
Two operators using a single ham operator repeater.
Yeah, it's just an analog FM repeater. There's no timing signal. There's nothing like that. It's just a frequency. Just like it's just like if your buddy was up there with a little kid's walkie-talkie and he's transmitting, and multiple people on the ground are receiving the same signal. If that same signal was being just the frequency was being changed to trick one person, everybody would see the frequency change. But because it's the same frequency everybody's receiving, then they can all tune their receivers up or down in frequency and get the Doppler shift, so they can tell the approach speed of
you're not saying anything different than what I'm saying. If it's already sent out with what it needs to be, that's what the ground receivers are going to interpret it, and they can facilitate that specifically through corrections. So you're not saying anything different from what I'm saying. So everyone's going to get the same signal, right? It's already offset relative to that position where it needs to be. So everyone's going to interpret it the way that it should be. Because it's already offset to that. So I don't.
Well,
your conclusion's my premise, man.
I think Jesse was just describing simple Doppler shift, wasn't he?
Yeah.
Yes.
Like,
So can I say something about it? So it seems like you described this Doppler shift as if the satellite was already like physically at the source changing the frequency of its signal to create that appearance of a Doppler shift here on the ground. But this doesn't make any sense because this Doppler shift doesn't only depend on a time. If you have multiple observers receiving a signal from the same satellite at the same time, and for one observer this satellite is approaching them, for another one this satellite is leaving the region, one will have like a higher frequency, another will have lower frequency at the same time.
I don't dispute relative Doppler shift. What I'm saying is that you can already offset it so that when it's interpreted, no one's going to know the difference. That mechanism, right? It already exists in the system because they make meridian corrections. So whether or not you like
Who's making the meridian correction?
You're going back to GPS now.
Every time a GPS station, or I'm sorry, every time. No, but the analogy is the same because he's talking about a source being emitted and then relative observers on the ground getting the same signal and being able to differentiate that it wasn't spoofed. What I'm saying is that the equivalence there is the same thing. If it's already off cooked, everyone's going to get the same thing and they're good to go. And you wouldn't know.
Like
and 1 second, you're saying like, whoa, you're way off base, buddy. It already exists through meridian corrections. When a space vehicle, quote unquote satellite, right, traverses 2D GPS stations, they send a signal to offset it. That makes the correction that changes that literally changes its position with timing. So this mechanism already exists within buddy. The mechanism already exists. I'm not going to listen to you say it. They don't have anything that I'm talking about when we're looking at a citation to start with that says behind the scenes calculations are done that make it comport to the globe. Like, wait, this, like, dude, just it's in the system. Whether or not you acknowledge it is up to you, dog.
No, I mean, I tagged you with a link to a specific details of a specific satellite we can talk about that's not a GPS satellite if you like.
Okay.
Jesse, let's let Jesse go because it was his question. Jesse, do you want to amplify more what you were talking about?
Maybe I'll just make a comment. It didn't seem like what I was saying was being understood at all. So maybe Alan and I can just talk about that sometime in private and kind of get to where we have, just a common understanding on the basics there. But yeah, basically the Doppler shift allows people to, and the Doppler shift, it can't be faked at the satellite because then it would fake it for everybody. If they increase the frequency by 5 kilohertz at the satellite, then that would increase it for everybody. The problem is it's increased for some people and decreased for others, and you can't do that at the same time on the same signal on the same analog repeater carrier wave. So yeah, but the point is we can measure the velocities, or the orbital period and the velocities of satellites going over, and we do find that they go different speeds at a given altitude. They go different speeds going east as compared to west as viewed from Earth, as if Earth is turning.
Well, that offset is done through timing, which is measured through the Sagnac effect. Remember how I said that the satellites require Sagnac corrections? They're making sidereal corrections. These are all facilitating the same thing. So it would appear that way, like, mathematically, right? But mechanistically, the Earth would be stationary and ether wind would be facilitating the same exact mechanism.
Well, there's no timing issues, or there's no timing to offset. It's like when you're standing by the highway and a car goes by with its horn blaring. At first, the pitch is higher. And
oh, Jesse, dude, I get what you're saying. It's already modulated the signal to be offset. So what everyone gets is the same thing. It's going to be like, we're not saying anything differently. And I'm losing patience listening to you describe the same thing that I'm describing while saying that I don't understand it. So
I don't.
Maybe we can wrap
like
up.
You're understanding it though, Alan. I will say that
it's sent from a single source. Everyone gets the same thing. How could it possibly be manipulated? It would be different for other people. It's just simply the relative Doppler shift. Is that about it? Guys,
No.
it's a different argument now.
It's always been the same argument. It needs to be described in a different way, it sounds like.
All right. Well, any other questions, comments, or concerns? He's using an analogy, Daza, right?
Well,
No
let me just say
singing in
thank you,
BC.
Alan.
Jesus.
No,
No
he's not
singing.
using an analogy. He's specifically discussing a particular case of a simple
Oh, that's
disk.
analogous to the fucking system
it's
that we're talking, dude.
Language.
Sorry, you're right.
Okay. So what's the difference between a GPS satellite and a space vehicle that's just a repeater for ham radios if they're both making meridian corrections?
They aren't, and that's the
Well, the ham isn't, right? That's the analogy, is that they're just saying that it just works with no corrections. They're not acknowledging the correction part, which would give an offset, which requires a mechanism to do the thing that I'm talking about, which they won't acknowledge, while saying that, but how come my ham radio the same?
So Jesse's point is that there's this Doppler shift that can only be described with Earth rotation. Is that what you guys are putting forth? That your
Well,
claim?
if two people will perceive a different Doppler shift, then how is it from the same signal? Then how does the satellite know what signal to emit to give
Well-
the is it emitting a different signal for each receiver?
No. And then no. And the difference in what you're talking about right now would be facilitated by the difference created by east-west differentials by ether wind. So rotation, right, would have an equivalent effect as the east-west bias for ether wind to produce the same thing. So when you say that, this difference, therefore earth ball move, well, no. Earth ball could be stationary and the difference could be created by the medium in which light's propagating through.
So the
So
ether wind
essentially, it's not mutually exclusive, is Alan's point.
So the ether wind both changes the frequency and moves around projectiles. Is that an accurate summation?
Well, in terms of moving around projectiles, that's yet to ever be demonstrated. What we were talking about earlier was the change in mass with respect to east-west differentials, which would be interesting. I haven't seen that yet. And
It's the Latos effect or whatever.
And the first part of your question was, what was the first part?
No, that was the first part.
Oh, I'm sorry. What was the second part then?
This Doppler shift example.
Oh, the Doppler shift example. Yeah, relative motion through a field will create that shift. I mean, so you got to think about this, right? So we have light on the ground or whatever, right? Presumably. And in the east-west directions, it's measuring a phase difference, right? Like the mechanism that's in, not only that, it's literally fluctuating by the second throughout the day, which, when you draw a sine wave or when you do a Fourier analysis on those min-max fluctuations, it makes a sine wave with respect to sidereal time. So we have this bias that's doing the same thing. Anyway, that would create Doppler shifts, relative motion through a field would create
both
that.
examples. Well, not both examples. The second example is using light. That's the thing. If you're using light, then you're basically, it's not mutually exclusive because what you could attribute to Earth rotation is what we attribute to ether wind. But the difference though is that if you have different Doppler shifts at different altitudes, how does that work with Earth rotation?
Well, they actually don't. They say, so get this, they make a uniform correction or whatever they say. They say that basically because the Earth's rotating through a uniform gravitational field, but the Earth's oblate, that there's a gravitational potential offset essentially like created through that, where they can treat the difference in gravitational potential between the two as an equipotential gradient, so they can just use the same correction. or I'm sorry, they can just use one uniform correction rather than like latitude dependent ones, for example. Like when the satellite is perihelion and aphelion, like Jesse was saying, how it goes up higher and lower. They can use the same correction for that. They can treat it the same.
All right. Any other questions, Jesse? Unless someone else was next.
On the same topic or a different topic?
I don't know.
Could I try an illustration, an analogy?
Sure.
Okay.
And then we'll wrap up on that. I think we've been going
All
for
right.
2 hours. Go ahead. You want a screen share?
No, it's just a verbal one. It's pretty simple. Let's
Gotcha.
say there was a long straight highway, and we've got cars going both ways, 50 miles an hour, 100 miles an hour, whatever, but the same speed. They're all going the same speed. And I'm standing by that highway, and there's a car coming towards me from one direction with his horn on, and a car coming towards me from the other direction, because it's a two-way highway, with his horn on. I will hear them both pitch shifted up the same amount, right?
Mm-hmm. Well, one will be higher, one will be lower. One's moving towards you, one's away.
No, they're both coming towards me at this point.
Oh, sorry. I thought you said, okay, yeah, go ahead.
Yeah, they're in opposite lanes. They're both coming towards me at 100 miles an hour with their horns on.
Mm-hmm.
If I were then to start moving along that highway, I would see that pitch shift deviate. One would go down and the other would go up, right?
Right.
And that's a perfect audio analogy of the radio wave thing that I'm talking about with the simple ham radio repeater.
Right. And if there was a medium, right,
that was
carrying the wave, doing the same thing, that same mechanism would be present, because that's actually what's measured. And radio waves are light. So same exact concept. All right.
But
yes.
But for the Doppler shift to be different, then that means there has to be a difference in velocity between me and car A and me and car B, right? A physical difference?
If you were using sound, yeah, sure.
But not radio waves?
Correct. Radio waves are influenced by, say it out loud with me, anyone? Ether wind.
But they still have a period and a frequency. And if the distance between me and the transmitter is not changing, I cannot have Doppler shift, right? The distance has to be changing for me to have Doppler shift, right?
Ooh, the wavelengths have to change, and that would be facilitated by going faster or slower, because the change in wavelength is inversely proportional to the frequency. So once the wavelength changes because of the velocity boost, it's going to have an inversely proportional effect on the frequency. Same exact mechanism, different interpretation, brother man.
Yep.
Am I good to roll out of here, brother?
Yeah.
Well, let's talk again another time, because I think we have some interesting things, but we're obviously out of time.
Absolutely. All right. Well, I'll see you for the Celestial Theodes Monday or whatever.
And one quick comment, and talking about the Eötvös effect.
Mhm.
You said the changing mass in the different direction, and no, it's the same mass. It's a different measured weight.
Oh, sorry. Thank you. Yes. Thank you for the correction.
Alan,
Yes.
I DM'd you a link to the Wikipedia article on Eötvös effect, just to give you a launching point on the topic.
TY, sir. All right. Well, thank you guys. Much appreciated. We will do future events.
Okay. Sounds good.
SpaceAudits.net for the merch.
All right, lads and ladettes. See you guys on the next episode.
All right.
All right, let's see here. Oh, where's my webcam at? Where did my camera? Oh, was I closed out? Oh, dude, haven't been on cam this entire time. Rip. All right, well, shout out to the boys in the chat. We will be here for tomorrow for community night. Friday community night at 8 p.m. Tune into that. See you guys tomorrow. Thanks everyone for tuning in, and thanks everyone for the support. Much appreciated. You guys are awesome. If you would like to contribute to the growth of Aether Cosmology, you can go to co-fi.com/space_audits, become a monthly subscriber, or you can buy the lifetime membership, which is a pledge of support for the boys. All right.